C2017 K2, a comet with an orbit stretching far beyond the outer reaches of the solar system, was first observed in May of 2017 by astronomers using the PANSTARRS 1 telescope in Hawaii. Its discovery was the culmination of an unexpected moment in the quest to explore the boundaries of our solar system. The comet had been travelling through space for billions of years, its icy nucleus untouched by the warmth of the sun until now. This distant wanderer had never before been observed by humans, having been too far from our world for any previous telescope to detect. When it was first spotted, it was still beyond the orbit of Neptune, a region of space known for hosting icy bodies far from the sun's warmth. Despite being so far from Earth, the comet's unusual trajectory made it an object of great scientific interest. Its orbit would soon bring it closer to the sun, and with that, scientists expected it would begin to show signs of the characteristic activity associated with comets. As it moved toward perihelion, the point in its orbit closest to the sun, the curiosity surrounding the comet grew exponentially. Researchers had the opportunity to study a comet unlike any other one that had been travelling through the cold void of space for millennia without the influence of solar heating. The significance of this comet lay not just in its discovery, but in the unique conditions under which it would reveal its behaviour. A comet like C2017 K2 was expected to provide valuable insights into the composition and activity of icy bodies that remained largely untouched by the sun's radiation bodies that could hold crucial information about the early solar system. What was most intriguing about C2017 K2 was its peculiar trajectory. While most comets follow elliptical orbits that bring them into the inner solar system in a predictable manner, C2017 K2's path appeared more erratic, a long slow curve that had brought it from the farthest reaches of the solar system. Its orbit suggested that it was a long-period comet, one that had originated in the distant Oort cloud, a spherical region of icy objects that surrounds the solar system at a distance far beyond Pluto. The fact that it was passing through the inner solar system for the first time in its long journey made its arrival even more remarkable. Unlike short-period comets, which make frequent visits to the sun and have been observed multiple times, long-period comets like C2017 K2 are relatively rare and often more difficult to study. Their orbits take them through the distant corners of the solar system, and by the time they reach the sun, they're often too faint to detect or too fleeting to capture much data. C2017 K2, however, was an exception. Its path brought it close enough to Earth to be studied with unprecedented clarity, allowing scientists to gather data on its behaviour as it approached the sun. It was a rare opportunity, one that provided an invaluable glimpse into the workings of distant comets and the processes that shape their activity. The first signs of the comet's activity became apparent as it neared the inner solar system. Even though it was still far from the sun, the nucleus of C2017 K2 began to show signs of outgassing, an indication that the comet was starting to warm up. The release of gas from the nucleus of a comet occurs when the sun's heat causes the ices that make up the comet's nucleus to vaporize. This process, known as sublimation, is what gives comets their signature tails. C2017 K2, however, showed an early onset of activity even before it reached the sun's warmth. This early outgassing was particularly unusual, as comets typically do not begin their visible activity until they are much closer to the sun, often around the distance of Jupiter's orbit. The fact that C2017 K2 started releasing gas so far from the sun raised intriguing questions about the composition and structure of its nucleus. What could explain this early activity? Could the comet be made of materials that were more volatile or sensitive to heat than those of typical comets? As C2017 K2 drew closer to the sun, scientists continued to monitor its behaviour, eager to learn more about the forces driving its early outgassing and what this might reveal about the comet's internal composition. The nucleus of a comet is a relatively small and compact object, typically measuring just a few kilometres across. Despite their small size, these nuclei are often made up of a complex mix of volatile ices, dust, and organic compounds. When a comet is far from the sun, the ices in the nucleus remain frozen, and the comet remains dormant with no visible activity. But as the comet approaches the Sun, the increase in solar radiation causes the ices to sublimate, releasing gas and dust into space. This outgassing process forms the comet's coma, a bright cloud-like halo that surrounds the nucleus and often a tail. The tail is made up of particles released from the nucleus carried away by the solar wind and radiation pressure. The size and shape of the coma and tail depend on the comet's activity level and the composition of its nucleus. C2017 K2's early outgassing suggested that it had a particularly volatile nucleus one that was sensitive to solar radiation even at great distances. This was a key observation that set the comet apart from others. It indicated that C2017 K2 might be a particularly active comet, one whose behaviour could provide valuable insights into the processes that govern cometary activity. As C2017 K2 drew closer to the Sun, its activity intensified. The comet's outgassing became more pronounced, and its coma began to grow larger, its structure becoming more complex. Scientists were able to study the comet using a range of telescopes, both on Earth and in space. These observations revealed a number of intriguing features, including a distinctive asymmetric coma, which suggested that the comet was releasing gas and dust in a non-uniform manner. This asymmetry was likely caused by the uneven heating of the comet's nucleus as it rotated. Comets like C2017 K2 rotate slowly, and as different parts of their nucleus face the Sun, they experience varying amounts of heat. This uneven heating can lead to differences in the rate of outgassing, causing parts of the coma to be more dense or diffuse than others. The presence of such features highlighted the complexity of the comet's activity and the dynamic nature of its interaction with the solar wind and radiation. It was clear that C2017 K2 was a comet that was not only active but unusually so far more so than typical comets at this stage of their orbits. What set C2017 K2 apart from other comets was not just its early activity but its size. The comet's nucleus was much larger than typical comets, measuring around 20 kilometers across, which made it one of the largest comets ever observed. This size likely contributed to its heightened activity. A larger nucleus means that there is more material available to sublimate, leading to a greater release of gas and dust. The large size of the nucleus also meant that C2017 K2 had a greater surface area for outgassing, which in turn contributed to its vibrant coma and tail. This size made the comet an even more interesting object of study, as it provided researchers with an opportunity to observe a particularly large and active comet in detail. The size of the nucleus also had implications for the comet's evolution. As it continued to move closer to the Sun, its activity was expected to increase, and scientists were eager to see how the comet would behave as it passed through the warmer regions of the solar system. Would it continue to exhibit such high levels of activity, or would the comet eventually settle into a more typical behaviour pattern as it neared perihelion? The discovery of C2017 K2 marked a significant moment in our understanding of comets. It was a reminder of how much remains to be discovered about these distant objects. Comets are among the oldest and most primitive bodies in the solar system, containing clues about the conditions in the early solar system and the processes that led to the formation of planets. By studying comets like C2017, K2 scientists hope to uncover new insights into the history of the solar system and the materials that make up its building blocks. C2017 K2 was not just a comet, it was a window into the past, a chance to observe the behaviour of an object that had been travelling through space for billions of years, largely unaffected by the heat of the Sun. As the comet continued its journey, scientists would remain focused on the data it provided, eager to learn more about the forces that shape these enigmatic visitors from the distant reaches of the solar system. C2017 K2's trajectory was an essential part of its story, one that set it apart from other comets. Its orbital path was unlike the typical comet, which follows a more predictable elliptical orbit that brings it into the inner solar system over regular intervals. C2017 K2, however, had an orbit that was much more elongated and stretched out, with its point of origin being the distant Oort cloud, a vast region of icy bodies surrounding the solar system at a distance far beyond the orbit of Pluto. The Oort cloud is thought to be the source of long-period comets, those that take hundreds or even thousands of years to complete one orbit around the Sun. Unlike short-period comets which visit the Sun frequently and can be studied over multiple passes, long-period comets are much more difficult to observe. They typically come into the inner solar system only once during their long orbits, making their appearance a rare event. C2017 K2 was no exception. Its orbit had brought it in from the farthest reaches of the solar system, and it would not return for millions of years. This long journey through space meant that C2017 K2 had been travelling for billions of years, without the influence of the Sun's radiation making its approach to the inner solar system particularly fascinating to astronomers. As the comet continued on its orbit, scientists tracked its path with increasing interest, noting that its passage through the solar system provided a rare opportunity to study a long-period comet in detail, something that had not been possible for many decades. The trajectory of C2017 K2 also had a significant impact on the timing of its activity. Unlike short-period comets, which often begin to exhibit signs of activity as they approach the outer planets, long-period comets like C2017 K2 tend to remain dormant until they come close to the Sun. As the comet's orbit took it toward perihelion, the point in its orbit where it would be closest to the Sun, scientists expected it to begin showing the typical signs of outgassing the release of gas and dust from the nucleus as it warmed. However, C2017 K2 began to exhibit signs of activity much earlier than anticipated. Even though it was still well beyond the orbit of Jupiter, the comet's nucleus was already releasing gas and dust. This early activity was particularly surprising because comets typically remain dormant until they are much closer to the Sun, usually around the distance of Jupiter's orbit. The early onset of outgassing suggested that C2017 K2 was composed of materials that were more volatile than those of typical comets. While many comets require the heat of the Sun to trigger their activity, C2017 K2 seemed to be more sensitive to the slightest increase in temperature. This unique characteristic made it a subject of great scientific interest, as it offered a chance to study how different materials behave in the early stages of a comet's approach to the Sun. As C2017 K2 continued its journey through the solar system, scientists closely monitored its path and activity. They were especially interested in understanding the forces that were driving its early outgassing. One of the key factors influencing a comet's activity is the Sun's radiation. As a comet moves closer to the Sun, the increase in solar radiation causes the volatile materials in the comet's nucleus to vaporize. This process, known as sublimation, is what causes the coma and tail of a comet to form. The more solar radiation a comet receives, the more gas and dust it releases. However, the amount of activity a comet exhibits is also influenced by the composition of its nucleus. Some comets are made up of more volatile materials which can sublimate at lower temperatures, while others contain materials that require more heat to vaporize. In the case of C2017 K2, its early outgassing suggested that its nucleus was composed of a particularly volatile mixture of ices and dust materials that were more sensitive to heat than those of typical comets. This raised important questions about the composition and structure of the comet's nucleus and how it compared to other long-period comets. Was C2017 K2 an anomaly, or did it represent a new class of comets with more volatile nuclei? The unusual trajectory of C2017 K2 also raised questions about the formation of the comet itself. It is believed that the Oort cloud, where C2017 K2 originated, is the source of long-period comets. The Oort cloud is a spherical region of space that extends far beyond the orbit of Pluto and contains a vast number of icy bodies. These objects are thought to be remnants from the early solar system leftover building blocks from the formation of the planets. Over time, the gravitational influence of nearby stars or the Sun itself can perturb the orbits of objects in the Oort cloud, sending them on a trajectory toward the inner solar system. Once they are close enough to the Sun, the heat causes them to become active and they begin to show the characteristic tails and comas of comets. C2017 K2's orbit suggests that it came from the outer reaches of the Oort cloud, a region of space that has been largely unexplored. By studying its trajectory, scientists hope to gain new insights into the formation and evolution of comets and the role that the Oort cloud plays in the dynamics of the solar system. Another intriguing aspect of C2017 K2's trajectory was the potential for future observations. The comet's orbit was such that it would not pass close to Earth again for millions of years, making this its only opportunity to study the comet in detail. While comets like C2017 K2 provide scientists with valuable insights into the early solar system, their brief appearance in the inner solar system makes them difficult to study. Once a comet completes its orbit and leaves the inner solar system, it becomes too faint to observe, and the opportunity to study it is lost. C2017 K2's trajectory was therefore a rare opportunity to observe a long-period comet up close, one that would not return for millions of years. For scientists, this brief window of observation was invaluable, as it allowed them to gather data on the comet's activity, its composition and its behavior as it passed through the inner solar system. As the comet's trajectory continued to unfold, scientists were eager to see how its behavior would evolve as it passed through the warmer regions of the solar system. Would C2017 K2 continue to show such high levels of activity, or would it eventually settle into a more typical pattern of cometary behavior? The comet's unusual trajectory and early signs of activity made it a fascinating object of study, one that held the potential to reveal new insights into the nature of comets and the processes that govern their behavior. Its passage through the solar system was a reminder of the dynamic nature of these distant visitors from the outer reaches of space and the fleeting opportunity they offer to learn more about the history of the solar system. As C2017 K2 approached the inner solar system, the comet began to exhibit clear signs of activity much earlier than anticipated. This early onset of outgassing visible from Earth through telescopic observation was one of the most striking features of the comet's behavior. The gradual increase in brightness marked the first hints of what would become a spectacular display of cometary activity as it moved closer to the Sun. In typical comets, activity begins to increase only when the object has moved within the orbit of Jupiter, as the Sun's radiation begins to heat the nucleus, causing the volatile ices within to sublimate. However, C2017 K2 displayed signs of activity even when it was still far beyond the orbit of Jupiter. This unexpected early outgassing was an intriguing aspect of the comet, and pointed to the possibility that its nucleus was composed of materials more easily triggered by solar radiation, or perhaps even that its ice had been preserved in a different state due to its long journey from the outer solar system. The signs of activity were first detected as faint increases in brightness, observed with ground-based telescopes, which suggested that the comet's nucleus was already beginning to release gas and dust. This gas, often made up of water, vapor carbon dioxide and other volatile compounds, formed the coma, a cloud of gas and dust surrounding the comet's nucleus. The coma is a hallmark of cometary activity, and its size and structure depend on the comet's distance from the Sun and the rate at which the nucleus releases material. As the comet continued its approach, the coma began to expand, becoming more visible and structured. The size of the coma, along with its uneven shape, suggested that C2017 K2 was releasing material at different rates across its surface. This asymmetry was likely a result of the uneven heating of the nucleus, as it rotated, with certain areas of the comet being exposed to more solar radiation at any given time than others. The unusual early activity of C2017 K2 raised important questions about the structure and composition of the comet's nucleus. Cometary nuclei are often composed of a mixture of water, ice, carbon dioxide, ammonia, methane, and dust, all of which are volatile and can sublimate when exposed to the heat of the Sun. However, the precise composition of any given comet can vary, and this difference in composition may influence the timing and intensity of its activity. The early onset of outgassing observed in C2017 K2 suggested that its nucleus might contain more volatile compounds than typical comets. Alternatively, the icy material on its surface may have been more easily affected by the solar radiation than that of other comets, even those at similar distances. This was an important clue for scientists who could use the comet's early activity to infer the kinds of materials it contained and how these materials interacted with solar energy. As C2017 K2 moved closer to the Sun, its outgassing became more intense. The comet's coma expanded rapidly, and the tail, which is formed from the gas and dust particles expelled from the nucleus, began to grow. This tail made up of particles blown away from the comet by the solar wind, and radiation pressure began to stretch out, becoming more visible. The tail's structure was determined by the interplay between the solar wind, the Sun's radiation pressure, and the amount of material being ejected from the comet's nucleus. The shape of the tail was constantly changing as the comet continued its journey toward perihelion. The gases released from the nucleus formed a glowing cloud which illuminated the particles that were caught in the solar wind. As the comet got closer to the Sun, the tail grew longer, sometimes taking on a distinct shape, and at other times appearing diffuse, stretched thin by the forces of the solar wind. The tail of a comet can sometimes become so large that it extends millions of kilometers into space. In the case of C2017 K2, this phenomenon was particularly pronounced as the comet's outgassing continued to increase with its approach to the Sun. One of the most fascinating aspects of C2017 K2's early activity was the composition of the coma and tail. Observations made by astronomers revealed that the coma contained a range of gases and dust particles, each with its own distinct properties. The gases emitted from the nucleus of C2017 K2 formed a cloud that glowed faintly, and as the comet continued its journey, this cloud became more structured with areas of higher and lower density. This unevenness was likely due to the varying rate of outgassing across the comet's surface, as well as the direction in which the comet was moving. The comet's orientation with respect to the Sun meant that different parts of the nucleus were exposed to the Sun's radiation at different times, leading to varying levels of sublimation across its surface. As the comet approached perihelion, the density and structure of the coma would become more pronounced, and the gas particles would spread out to form a tail behind the nucleus. The formation of the tail is a key feature of any comet. As the comet moves through space, the Sun's radiation causes the ices in the nucleus to sublimate, turning into gas that is pushed away by the pressure of sunlight. This process creates a tail that always points away from the Sun, regardless of the direction in which the comet is travelling. The tail's size and structure are determined by a variety of factors, including the amount of material released from the nucleus, the speed of the solar wind, and the intensity of solar radiation. For C2017 K2, the tail was particularly large, reflecting the high level of activity the comet was experiencing. The tail's shape changed over time, growing longer as the comet neared perihelion and becoming more diffuse as the forces acting on it varied. While most comets' tails are composed primarily of gas, C2017 K2's tail contained a substantial amount of dust particles, which were released from the nucleus as the comet warmed. These particles, though small, contributed to the tail's brightness and appearance. The presence of dust in the tail also played a role in how the tail reacted to the solar wind. The dust particles were pushed by the wind, creating the characteristic shape of the comet's tail, which was always directed away from the Sun. As the comet continued to approach the Sun, astronomers worked to monitor its behaviour, noting the changes in the size and shape of the coma and tail. The heightened activity provided valuable insights into the processes that govern cometary behaviour and how comets interact with solar radiation. The behaviour of C2017 K2 was consistent with what scientists expect from a highly active Comet 1 that was undergoing intense sublimation and outgassing. The fact that the comet began its activity at such an early stage in its journey through the solar system raised questions about the nature of its materials and its interaction with the Sun's radiation. As more observations were made, scientists began to refine their understanding of what made C2017 K2 unique. It was clear that the comet was a rare example of a long-period comet with an early intense burst of activity, and it provided a window into the behaviour of comets from the outer reaches of the solar system. The nucleus of a comet is a small icy body that serves as the core from which all cometary activity originates. Although it can be difficult to observe directly due to its distance and faintness, understanding the composition and structure of the nucleus is essential to understanding the behaviour of a comet like C2017K2. A typical comet nucleus is made up of a mixture of volatile ices, including water, ice carbon dioxide, methane, and ammonia, along with dust particles. These ices are held together by gravity in a loose porous structure often referred to as a dirty snowball. When a comet approaches the Sun, the heat causes these ices to sublimate, transforming them directly into gas without first becoming liquid. This process creates the coma, the halo of gas and dust that surrounds the nucleus, and the tail which forms as material is blown away from the nucleus by the solar wind and radiation pressure. However, the exact composition and structure of a comet's nucleus can vary from one object to another, and this variability has significant implications for the comet's activity and appearance. In the case of C2017, K2 early observations suggested that its nucleus was much larger than typical comets. While many comets have nuclei that measure only a few kilometers across C2017, K2's nucleus was estimated to be about 20 kilometers in diameter. This size made it one of the largest comets observed, which was significant for several reasons. The larger the nucleus, the more material is available to sublimate, leading to more intense outgassing, and in turn more pronounced activity. A larger nucleus also means that the comet has a greater surface area from which material can be released, contributing to a more prominent coma and tail. The size of C2017 K2's nucleus likely contributed to its early outgassing and the intensity of its activity as it approached the Sun. This large nucleus made the comet one of the most active observed, as it provided a greater source of volatile materials that could sublimate and contribute to the growing coma and tail. Its size also gave scientists a unique opportunity to study the behaviour of a large active comet in detail. The structure of a comet's nucleus is also an important factor in determining its activity. Cometary nuclei are thought to be composed of a mix of ice and dust particles that are loosely bound together. The exact arrangement of these materials can vary, and this can influence how a comet behaves as it approaches the Sun. Some comets may have nuclei that are more solid with fewer voids or pockets of gas, while others may have more porous structures allowing gas to escape more easily. The degree of porosity in a comet's nucleus plays a role in how efficiently the ice sublimates and how much gas is released into space. For C2017K2, the early outgassing suggested that its nucleus might be composed of more volatile materials than those found in typical comets, or it could have a more porous structure that allowed gas to escape more readily. The precise structure of the nucleus is difficult to determine without direct observations, but the early onset of activity suggests that C2017K2 had characteristics that made it more sensitive to solar radiation than other comets. Another factor that contributes to the activity of a comet is its rotation. Like most comets, C2017K2 is rotating, albeit slowly, and this rotation has a significant impact on the outgassing process. As the comet rotates, different parts of the nucleus are exposed to sunlight at different times, and this uneven exposure leads to variations in the rate of sublimation. The parts of the nucleus that are directly facing the Sun receive more heat, causing the volatile materials in those areas to sublimate more quickly. Meanwhile, the areas of the nucleus that are in shadow are not heated as intensely, and therefore experience less sublimation. This uneven heating can cause the coma to be uneven as well, with certain parts of the coma being denser than others, reflecting the varying rates of outgassing across the comet's surface. In the case of C2017K2, the coma appeared to have a distinct asymmetry, which likely reflected the uneven heating of the nucleus as it rotated. This asymmetry provided valuable information about the rotation and structure of the comet's nucleus, suggesting that its composition and surface characteristics were contributing to the early and intense outgassing observed. The early onset of activity observed in C2017K2 also raised questions about the preservation of its icy materials. Comets are often thought to be remnants of the early solar system, containing material that has remained largely unchanged since the formation of the solar system billions of years ago. This pristine nature makes comets valuable objects of study, as they provide a glimpse into the conditions of the early solar system. However, as comets approach the Sun, their icy surfaces begin to sublimate, and over time this process can lead to the loss of volatile materials. The early activity of C2017 K2 suggested that its icy materials were more easily vaporized than those of other comets, which raised the possibility that its nucleus contained volatile compounds that had been preserved in a different state during its long journey through space. These preserved materials might have been more sensitive to solar radiation, or might have been composed of different ices that sublimated at lower temperatures. Understanding how the icy materials in C2017 K2's nucleus behaved as it approached the Sun provided scientists with valuable insights into the processes that govern the preservation and alteration of cometary material. The study of the nucleus of C2017 K2 is an important part of understanding the comet's activity and behavior. By examining the size, structure, and composition of the nucleus, scientists can learn more about the conditions under which the comet formed and how its materials interact with the Sun's radiation. The large size of C2017 K2's nucleus, along with the early signs of outgassing, suggested that the comet was not like typical comets, and its study could provide new insights into the nature of long-period comets. The comet's nucleus might contain clues about the early solar system, such as the types of ices and dust that were present in the primordial solar nebula, and how these materials were affected by the processes that led to the formation of the planets. Studying the nucleus of C2017 K2 therefore offers a rare opportunity to investigate a comet from the distant reaches of the solar system and to learn more about the building blocks of the solar system itself. This knowledge could help scientists better understand the processes that govern the behavior of comets and their role in the evolution of the solar system. In the case of C2017 K2, the comet's early activity and the unique characteristics of its nucleus made it a valuable subject of study. The large size of its nucleus, along with its composition and structure, contributed to the intensity of its activity as it approached the Sun. This early outgassing was not just a curiosity, but a key to understanding the comet's internal processes and how they interact with solar radiation. As C2017 K2 continued its journey toward perihelion, astronomers were eager to learn more about its nucleus and to observe how its activity would evolve. The study of the comet's nucleus was an essential part of the larger effort to understand comets and their role in the history and evolution of the solar system. Through continued observation and analysis, scientists hope to uncover more about the processes that govern cometary activity and the nature of the icy bodies that orbit the Sun. As C2017 K2 continued its journey through the solar system, one of the most striking features of its behavior became clear: the unprecedented level of activity it exhibited as it neared the Sun. Unlike typical comets, which gradually begin to show signs of outgassing as they approach the inner solar system, C2017 K2 displayed an extraordinary intensity of activity much earlier than expected. The comet's outgassing became more pronounced as it moved closer to the Sun, and by the time it reached the vicinity of Jupiter, the intensity of its activity was remarkable. This heightened activity was not only a surprise, but also a significant departure from the typical behavior of comets at similar distances from the Sun. For scientists studying the comet, it provided an opportunity to investigate a comet that was showing far more activity than others at a similar stage in their orbits. The early onset of activity combined with the intensity of the outgassing suggested that C2017 K2 was not like most comets. It was far more active, and this presented a fascinating puzzle for researchers. The cause of C2017 K2's unusual activity lay in its composition and the conditions that governed its outgassing. The nucleus of the comet, which was much larger than typical comets, provided a greater surface area for outgassing. This larger surface area meant that more material could sublimate, as the comet approached the Sun, resulting in a more pronounced coma and tail. As the comet continued its journey, it released gas and dust particles in large quantities, which created the bright coma and tail that became visible through telescopes. The tail, made up of gas and dust particles, stretched out as the comet's motion took it toward the Sun, growing larger and more visible with each passing day. The size of the tail was a direct result of the intensity of the outgassing, which was driven by the solar radiation affecting the volatile ices in the comet's nucleus. The closer the comet came to the Sun, the more intense the outgassing became and the larger the coma and tail grew. The increase in activity also had significant implications for the comet's overall structure. As C-2017 K2's coma expanded, it began to display a complex irregular shape with regions of higher and lower density. This irregular shape was likely due to the uneven release of gas and dust from the nucleus as it rotated. The uneven heating of the nucleus caused by its rotation meant that different parts of the surface were exposed to solar radiation at different times, leading to varying rates of sublimation. Some parts of the nucleus released gas and dust more rapidly than others, which caused the coma to develop an asymmetrical structure. This asymmetry was a key characteristic of C-2017 K2's outgassing and provided valuable clues about the internal structure and composition of the nucleus. Scientists could infer that the comet's surface was not uniform and that its internal composition might be more heterogeneous than initially thought. This was an important discovery as it suggested that C-2017 K2 was a particularly dynamic comet with an internal structure that influenced its behavior in unique ways. The irregular structure of C-2017 K2's coma was not just a superficial feature, it reflected the complex processes at work within the comet's nucleus. As the volatile ices within the nucleus sublimated, they were released into space in the form of gas and dust particles. These particles, which included water vapor, carbon dioxide, and other compounds, formed the coma, and as they were carried away by the solar wind, they formed the tail. The tail of a comet is always directed away from the Sun due to the pressure of sunlight on the gas and dust particles. As the solar wind carried these particles away from C-2017 K2, the tail grew longer and more diffuse. The larger the nucleus, and the more volatile the material inside it, the more material is released into space, leading to a larger and brighter tail. C-2017 K2's unusually large nucleus contributed to its intense outgassing, which in turn led to a tail that was much larger and more prominent than those of many other comets. The presence of dust particles in the tail also provided insight into the composition of the comet. In addition to gas, comets release small solid particles, often composed of dust and rocky material, which are carried away by the solar wind and radiation pressure. These particles, though tiny, contribute to the brightness and appearance of the comet's tail. The dust particles released from C-2017 K2's nucleus were responsible for the bright visible tail that stretched out behind the comet. As the solar wind pushed these particles away from the nucleus, they scattered sunlight, creating the visible tail. The interaction between the dust and the solar wind also influenced the tail's shape, causing it to stretch and curve in response to the changing forces acting on it. This dynamic interaction between the dust particles and the solar wind was a key factor in shaping the comet's tail and providing scientists with a visual record of the comet's activity. In addition to the tail and coma, scientists were also able to study the gas released from the comet using spectroscopic techniques. These observations allowed researchers to analyze the chemical composition of the gas and learn more about the materials present in C-2017 K2's nucleus. The gas released from a comet is a valuable source of information because it contains a mixture of volatile compounds, such as water vapor, carbon dioxide, and methane, as well as organic compounds and other chemicals. By analyzing the spectral lines of the gas, scientists could identify the specific compounds present and determine their relative abundances. This information provided a glimpse into the composition of C-2017 K2's nucleus and helped researchers understand how the comet's materials were interacting with solar radiation. The chemical makeup of the gas released by C2017K2 was an important clue in determining the composition of its nucleus and understanding how comets behave as they approach the Sun. The unprecedented activity of C2017K2 also raised questions about the factors that influence cometary outgassing. Why did this comet exhibit such early and intense activity, while others at similar distances from the Sun remained dormant? The answer likely lies in the specific composition of C2017K2's nucleus. The presence of more volatile materials or a more porous structure that allowed gas to escape more easily might explain why the comet began its outgassing at such a great distance from the Sun. Understanding the factors that influence a comet's activity is critical for understanding the behavior of these distant objects and the processes that govern their interaction with the solar radiation. C2017K2's behavior provided a rare opportunity to observe a highly active long-period comet and to study the complex processes that drive cometary outgassing. The heightened activity of C2017K2 also had implications for future observations of other comets. By studying this unusual comet in detail, scientists gained new insights into the factors that influence cometary behavior and the characteristics of long-period comets. The early and intense activity of C2017K2 demonstrated the importance of monitoring comets at all stages of their journeys through the solar system. Even comets that are far from the Sun can exhibit significant activity, and studying these objects in detail can provide valuable information about their composition and behavior. C2017K2's early activity may have been an anomaly, but it also served as a reminder of how much we can learn from observing comets in their natural environment. With continued observations and studies, scientists can refine their understanding of how comets evolve as they travel through the solar system and how their activity is influenced by the solar radiation they encounter. C2017K2's nucleus, a central component of its activity, not only distinguished the comet by its early onset of outgassing, but also by its size. At approximately 20 kilometers in diameter, C2017K2's nucleus was much larger than that of a typical comet, whose nucleus generally ranges from 1 to 5 kilometers across. This larger size had several important implications for the comet's behavior. First, a larger nucleus means that more material is available to sublimate, which can lead to a greater release of gas and dust. The result is a more substantial coma, the cloud of gas and dust surrounding the nucleus, and a larger tail. The greater the surface area of the nucleus, the more material can be released into space, which directly contributes to the comet's brightness and the size of its tail. C2017K2's significantly larger size made its activity more pronounced compared to typical comets of similar composition, and provided scientists with a rare opportunity to study a comet with such intense activity at this stage of its approach to the Sun. The sheer size of C2017K2's nucleus also suggested that the comet was in a different stage of its life compared to smaller comets. The nucleus of a comet is considered its core made up of ices, dust, and other compounds that have been preserved for billions of years. Over time, as comets pass through the inner solar system and experience repeated heating from the Sun, they lose material from their surface through sublimation. The more material that is lost, the smaller the nucleus becomes. A large nucleus like C2017K2's indicates that it may be a relatively young comet, or at least one that has undergone less sublimation in its long journey through the solar system. This is because larger comets typically start out with more material, which allows them to maintain their size for a longer period. However, the large size also meant that C2017K2 could continue to experience significant outgassing for a longer time than smaller comets. As the nucleus released gas and dust into space, the comet's coma and tail grew in size, leading to greater visibility and allowing astronomers to track its activity with greater precision. In addition to its size, the composition of C2017K2's nucleus likely played a critical role in its heightened activity. The typical composition of a comet's nucleus includes water, ice carbon dioxide, methane, ammonia, and other volatile compounds that can sublimate when exposed to the Sun's heat. However, the precise mixture of these materials can vary from comet to comet. The early outgassing of C2017 K2, observed well before it reached the inner solar system, suggested that its nucleus contained a greater proportion of volatile materials than most comets. This increased volatility could explain why the comet began to show signs of activity at such an early stage in its orbit. Comets that are more volatile tend to start sublimating at greater distances from the Sun, while less volatile comets remain dormant until they reach the warmer regions of the solar system. The increased activity of C2017 K2 also indicated that the volatile materials within the nucleus might be more easily vaporized than in typical comets, possibly due to the specific composition of the ices and dust it contained. The ability of C2017 K2 to release gas and dust at such a great distance from the Sun highlighted how the chemical makeup of the nucleus could influence the timing and intensity of a comet's activity. C2017 K2's large nucleus combined with its early activity offered a unique opportunity to observe a comet in its infancy. Typically, comets are first studied when they approach the inner solar system, where their activity becomes more pronounced. However, C2017 K2 was observed while it was still far from the Sun, at a distance where most comets would remain dormant. This early detection allowed scientists to study the comet's outgassing behavior at a time when other comets might not yet have shown any signs of activity. Understanding the relationship between the size composition and activity of the nucleus could provide important insights into the processes that govern cometary behavior. The study of C2017 K2's nucleus could help scientists learn more about the conditions under which comets form, how they evolve over time, and how the materials in their nuclei are affected by solar radiation. As C2017 K2 continued to approach the Sun, its outgassing would likely intensify. The heat from the Sun would cause more of the volatile materials in the nucleus to sublimate, increasing the amount of gas and dust released into space. The intensity of the outgassing would increase as the comet reached perihelion, the point in its orbit closest to the Sun. At perihelion, comets typically experience their most active phase as the Sun's radiation heats the nucleus to the point where sublimation is at its peak. The process of outgassing not only forms the coma and tail, but it also contributes to the evolution of the nucleus. Over time, as material is lost from the surface of the nucleus, the comet becomes smaller and its activity decreases. However, C2017 K2's larger nucleus meant that it would be able to sustain its activity for a longer period before the loss of material significantly impacted its outgassing behavior. The size and composition of C2017 K2's nucleus also played a role in determining the characteristics of its coma and tail. The coma, the cloud of gas and dust surrounding the nucleus, formed as a result of the sublimation of ices from the surface. The gas and dust were carried away from the nucleus by the pressure of sunlight and the solar wind, which caused the coma to expand and the tail to form. The shape and size of the coma and tail were influenced by the rate of outgassing, the amount of material being released from the nucleus, and the interactions between the solar wind and the gas and dust particles. C2017 K2's larger nucleus allowed it to release more material, which contributed to the growth of a larger and brighter coma and tail. The structure of the coma and tail could change over time, as the comet's orbit took it closer to the Sun and the intensity of its activity increased. The dust particles in the tail could scatter sunlight, creating a visible glow, while the gas in the coma formed a diffuse cloud-like structure around the nucleus. The study of C2017 K2's nucleus provided scientists with valuable insights into the composition and behavior of comets. Its large size, early onset of activity, and distinctive coma and tail made it a prime subject for observing the dynamics of cometary outgassing. By examining the physical characteristics of the nucleus and the materials it released into space, scientists could refine their understanding of the processes that govern cometary activity. The behavior of C2017 K2 could also shed light on the broader questions of cometary evolution and the factors that influence the formation and composition of comet nuclei. The comet's unusual activity, driven in part by its size and volatile composition, made it a unique and valuable object of study, offering a rare opportunity to observe a comet at an early stage in its journey through the solar system. C-2017 K2's nucleus, along with its increased activity and early outgassing, provided critical information about the nature of comets and the processes that drive their behavior. Its large size, volatile composition and dynamic activity made it one of the most fascinating comets observed in recent years. Through continued study of C-2017, K2 scientists were able to gain deeper insights into the behavior of comets from the outer reaches of the solar system and the complex interplay between a comet's nucleus and the forces of the solar system. These observations helped refine our understanding of comets as remnants from the early solar system, holding clues to the conditions that prevailed in the formation of the solar system itself. As C-2017 K2 continued its path toward the Sun, the role of solar heating became increasingly important in driving its activity. The Sun, as the primary source of energy for a comet, plays a pivotal role in the process of sublimation, the transformation of solid ices into gas as they absorb heat. This process is responsible for the characteristic features of a comet, including its coma and tail. The solar heating that causes the volatile materials in a comet's nucleus to sublimate is not uniform. As a comet approaches the Sun, different parts of its nucleus are exposed to varying degrees of solar radiation, depending on the orientation of the nucleus and its rotation. This uneven exposure results in asymmetric outgassing, where some areas of the comet's surface release gas and dust at a higher rate than others. The intensity of solar heating also affects the rate of sublimation and the amount of gas and dust released. For C-2017 K2, this uneven heating contributed to its unique outgassing behavior, which had been observed well before it reached the inner solar system. The process of sublimation begins as the comet's icy surface absorbs solar radiation. The ice is composed primarily of water, carbon dioxide, methane, ammonia, and other volatile compounds begin to heat up and vaporize. This vaporization causes the formation of the coma, a cloud of gas and dust surrounding the nucleus. As the comet gets closer to the Sun, the heat increases, causing more ices to sublimate and resulting in a larger and brighter coma. The gas and dust particles released from the nucleus are then carried away by the solar wind and radiation pressure, forming the tail of the comet. The tail always points away from the Sun, a result of the forces acting on the gas and dust particles as they are pushed by the solar wind. The longer the tail, the more intense the outgassing, and the closer the comet is to the Sun. For C-2017 K2, the intense early outgassing was directly linked to the amount of solar radiation it was absorbing, even though it had not yet passed close to the Sun. Solar heating plays a crucial role not only in triggering outgassing, but also in determining the overall activity of a comet. The more the comet is heated, the greater the rate of sublimation, and the more material is released into space. This leads to an increase in the size and brightness of the coma, as well as the expansion of the tail. The tail's size and shape are determined by several factors, including the amount of gas and dust being released from the nucleus, the strength of the solar wind, and the comet's proximity to the Sun. As C-2017 K2 moved closer to perihelion, the point in its orbit closest to the Sun, solar heating would become even more intense, and the comet's activity would increase further. This increase in activity would be visible in the growing coma and tail as the comet reached the peak of its outgassing phase. One of the key characteristics of C-2017 K2's activity was the early onset of outgassing. Most comets begin to show signs of activity only when they come within the orbit of Jupiter, but C-2017 K2 started releasing gas and dust well before reaching this point. This early activity suggested that the comet's surface was composed of more volatile materials than those of typical comets. The volatile ices that made up the nucleus of C-2017 K2 were likely more easily vaporized by the Sun's radiation than the ices in other comets. This meant that the comet began to show signs of activity at a greater distance from the Sun than expected. As the comet drew closer to the Sun, the outgassing would continue to intensify, and more gas and dust would be released into space. This early outgassing provided a unique opportunity to study a comet before it reached its most active phase, giving scientists valuable insights into the behavior of comets from the outer reaches of the solar system. In addition to the early onset of outgassing the intensity of C-2017, K2's activity was also influenced by the composition of its nucleus. Cometary nuclei are made up of a mixture of volatile ices, dust, and organic compounds. The specific composition of a nucleus can vary from comet to comet, and this variation can influence the rate of sublimation and the overall activity of the comet. Some comets, such as C-2017 K2, may have a higher proportion of volatile ices that can sublimate at lower temperatures. These more volatile ices cause the comet to become active at an earlier stage in its orbit, even before it reaches the warmer regions of the solar system. Other comets may contain less volatile ices, which means they do not begin outgassing until they are much closer to the Sun. The composition of C-2017 K2's nucleus was a critical factor in determining its early and intense activity, and understanding this composition helped scientists gain insights into the processes that govern the behavior of long-period comets. The solar heating of C-2017 K2's nucleus also had an impact on the structure of its coma and tail. As the comet's surface heated up, different areas of the nucleus began to sublimate at varying rates. This uneven heating caused the coma to develop an irregular shape with areas of higher and lower density. The parts of the nucleus that were exposed to more solar radiation released gas and dust at a faster rate, creating denser regions within the coma. This asymmetry in the coma was one of the key features of C-2017 K2's activity, and provided important clues about the nature of its nucleus. As the comet approached the Sun, the asymmetric outgassing would become more pronounced, and the coma and tail would continue to evolve in response to the changing solar conditions. The solar heating of C-2017 K2 also played a role in the expansion of its tail. As the comet got closer to the Sun, the tail grew larger and more visible, with the dust and gas particles being pushed farther away from the nucleus by the pressure of sunlight and the solar wind. The tail always pointed away from the Sun, and as C-2017 K2's activity increased, the tail grew longer and more diffuse. The intensity of the outgassing and the strength of the solar wind contributed to the tail's size and shape. The larger the tail, the more material was being ejected from the nucleus, and the more intense the comet's activity. C-2017 K2's large size and early outgassing meant that its tail would be particularly pronounced as it approached perihelion, providing a dramatic visual display for astronomers and observers on Earth. The role of solar heating in C-2017 K2's activity emphasized the importance of understanding the interaction between a comet and the Sun. Solar radiation is the primary driver of a comet's behavior, and the amount of heat a comet absorbs determines the rate at which it releases gas and dust. This process, known as sublimation, is central to the formation of a comet's coma and tail. The more intense the solar radiation, the more material a comet will release, leading to a brighter and more visible coma and tail. For C-2017 K2, the intense early outgassing was a direct result of its interaction with the Sun's radiation, which heated the volatile ices in its nucleus and caused them to sublimate. As the comet moved closer to the Sun, its activity would continue to intensify, and its coma and tail would grow, providing a striking visual display of the forces at work within the solar system. C-2017 K2's early activity and the role of solar heating highlighted the dynamic nature of comets and the complex processes that govern their behavior. The Sun's energy drives the sublimation of ices and the release of gas and dust, creating the coma and tail that characterize a comet. As the comet approached the Sun, the interaction between the nucleus and solar radiation became more pronounced, leading to greater activity and a larger, more visible tail. The study of C-2017 K2 provided valuable insights into how comets behave as they interact with the solar wind and solar radiation, and it contributed to our broader understanding of the processes that govern the evolution of comets in the solar system. As C-2017 K2 neared the Sun, the phenomenon of outgassing became even more pronounced. This process of outgassing is central to the formation of a comet's coma and tail, with solar energy being the driving force. The Sun's radiation causes volatile compounds within the comet's nucleus, such as water, carbon dioxide, and methane, to sublimate, turning them from solid ices directly into gas. As the gas escapes from the nucleus, it drags along with it dust particles that have been released from the surface. These materials are pushed away from the nucleus by the pressure of sunlight and the solar wind, forming the visible coma and tail. For C2017 K2, this process was particularly intense due to its early activity, which had already been detected before the comet had even reached the orbit of Jupiter. Unlike most comets, which typically begin to show activity only when they are much closer to the Sun, C2017 K2's early outgassing was a notable feature. This early release of gas and dust suggested that the comet's nucleus contained materials that were highly volatile, capable of sublimating at lower temperatures than those of typical comets. This gave rise to a particularly active and vibrant comet, visible even at greater distances from the Sun. When C2017 K2's outgassing increased the coma, the cloud of gas and dust surrounding the nucleus grew in size. The coma is made up of the materials being released from the comet as it moves through space. These materials include water vapor, carbon dioxide, and other volatiles, along with dust particles that contribute to the visible glow of the coma. As the comet got closer to the Sun, the release of gas and dust intensified, causing the coma to expand further. For C2017 K2, the size and brightness of its coma increased rapidly as it continued to release a significant amount of gas and dust into space. As with most comets, the gas that forms the coma was subjected to the forces of the solar wind, which pushed the material outward and created a halo of gas around the nucleus. The dust particles that were released from the nucleus also played a key role in the formation of the coma, scattering sunlight and adding to the overall visibility of the comet. This process was a clear indication of the comet's high activity level, as the size of the coma continued to grow with its approach to the Sun. The tail of C2017 K2, made up of gas and dust particles, followed a similar process. The solar wind carried the particles away from the nucleus, forming a tail that pointed away from the Sun. The interaction between the solar wind and the material released from the comet was responsible for shaping the tail, creating the long trailing structure that is characteristic of most comets. The size and shape of the tail varied depending on the amount of material being ejected from the nucleus and the intensity of the solar wind. As C2017 K2 continued its approach toward perihelion, the point in its orbit closest to the Sun, its tail grew longer and more diffuse. The increasing outgassing combined with the pressure of sunlight and the solar wind caused the particles in the tail to stretch out, creating a visible trail that followed the comet's path through space. The longer the tail, the more material was being released from the nucleus, and the greater the comet's activity. In C2017 K2's case, the tail became particularly pronounced as the comet neared perihelion, reflecting the intensity of the outgassing and the comet's unique composition. In addition to the gas and dust that form the coma and tail comets, like C2017 K2, also release a range of other materials, including organic compounds. These organic materials, often referred to as prebiotic molecules, have been of great interest to scientists because they offer clues about the chemical building blocks of life. The presence of these molecules in the coma and tail of C2017 K2 could provide valuable information about the composition of the early solar system and the materials that may have contributed to the formation of life on Earth. By studying the spectral lines emitted by the gases released from C2017, K2 scientists were able to identify the specific compounds present in the comet's coma. This information helped refine our understanding of the chemical makeup of comets and the role that these objects play in the broader context of the solar system's evolution. The release of gas and dust from C2017 K2 was also influenced by the specific conditions of the comet's orbit. As the comet moved close to the Sun, the intensity of the solar radiation increased, leading to a greater rate of sublimation and consequently more outgassing. This process was particularly evident in C2017 K2, as its early activity suggested that its nucleus was unusually volatile. The comet's early release of gas and dust suggested that the materials within its nucleus were more easily vaporized than those in other comets, leading to the intense outgassing observed from the very beginning of its approach. This was in contrast to most comets, which do not begin to show significant activity until they are much closer to the Sun. C2017 K2's unusual behavior provided a unique opportunity to study the sublimation process and the factors that influence the rate of outgassing in comets. Understanding these processes is crucial for understanding the behavior of comets and the role they play in the solar system. One of the remarkable features of C2017 K2's outgassing was the asymmetry observed in its coma. The uneven release of gas and dust from different parts of the nucleus caused the coma to have a distinct lopsided shape. This asymmetry was likely the result of the uneven heating of the nucleus, as it rotated, with some areas being exposed to more solar radiation than others. This uneven heating caused certain areas of the nucleus to release gas and dust at a higher rate, leading to the irregular shape of the coma. The shape of the coma provided scientists with valuable information about the internal structure and composition of the comet's nucleus. It suggested that the nucleus was not uniform, and that the release of material was influenced by the specific characteristics of the surface, such as its porosity and the distribution of volatile materials. As C2017 K2 continued its journey toward perihelion, the intensity of its outgassing would continue to increase, leading to further growth of the coma and tail. The process of sublimation would continue to release gas and dust into space, and the tail would grow longer, reflecting the increasing activity of the comet. The visible tail of C2017 K2 was a clear indication of the intense forces at work within the comet's nucleus, as the sun's radiation heated the volatile ices and caused them to sublimate. The interaction between the comet and the solar wind was also a key factor in shaping the tail, as the solar wind pushed the gas and dust away from the nucleus, creating the long trailing structure that followed the comet's path. The outgassing of C2017 K2 was a reminder of the dynamic nature of comets and the processes that govern their behavior. Solar heating, sublimation, and the interaction with the solar wind all played key roles in shaping the comet's coma and tail. The early onset of activity in C2017 K2 and its unusual outgassing behavior made it an important subject for study, offering insights into the processes that drive cometary activity and the factors that influence their behavior as they travel through the solar system. As the comet continued its journey toward perihelion, scientists eagerly watched its increasing activity, hoping to gain even more insights into the nature of comets and their role in the solar system's evolution. The tail of a comet is one of its most iconic features, a glowing trail of gas and dust that stretches out into space, always pointing away from the sun. The size, shape, and appearance of a comet's tail depend on a variety of factors, including the amount of gas and dust released from the nucleus, the speed of the solar wind, and the comet's proximity to the sun. C2017 K2, with its early and intense outgassing, produced a particularly notable tail. As the comet approached perihelion, the point in its orbit closest to the sun, its tail grew longer and more pronounced. This growth was a direct result of the increasing activity as the comet's volatile ices sublimated in response to the sun's radiation. The tail formed from the gas and dust particles expelled from the nucleus and carried away by the solar wind. The pressure from sunlight and the solar wind pushed these particles away from the comet, causing the tail to stretch and extend behind it. The structure of a comet's tail is determined by the interplay between the gas and dust particles released from the nucleus and the forces exerted on them by the sun. Solar radiation pressure pushes the lighter dust particles away from the nucleus, forming the bright visible tail. Meanwhile, the gas particles, which are more responsive to the solar wind, form a less visible but still prominent component of the tail. The shape and length of the tail depend on how much material is being released and how the solar wind interacts with the particles. For C2017 K2, the large amount of gas and dust being released from its nucleus created a tail that grew increasingly large as the comet neared the sun. The tail was not only longer but also more diffuse, reflecting the continuous release of gas and dust as the comet's outgassing intensified. The increasing size and visibility of the tail were clear signs of the comet's heightened activity, which was a result of the volatile composition of its nucleus and the intense solar heating it was experiencing. The tail of C2017K2 also displayed some unique features, including a noticeable asymmetry. The asymmetry was likely caused by uneven outgassing from the nucleus, which in turn affected the distribution of particles in the tail. As different parts of the nucleus were exposed to varying degrees of solar radiation, the rate of sublimation varied, leading to an uneven release of gas and dust. This uneven release resulted in a tail that was not perfectly symmetrical, with one side potentially appearing brighter or more diffuse than the other. The asymmetric tail was an important feature for scientists studying the comet, as it provided further insight into the internal structure and composition of the nucleus. The fact that the tail displayed such irregularities suggested that C2017K2's surface was not uniform, and that its outgassing behavior was influenced by factors such as the distribution of volatile ices and the comet's rotation. As C2017K2 moved closer to the Sun, the tail continued to evolve. The release of gas and dust accelerated as the comet reached perihelion, and the tail grew even more pronounced. The dust particles that had been released from the nucleus became more visible as they were pushed away from the comet by the pressure of sunlight. These particles scattered sunlight, making the tail glow brightly in the night sky. The longer the tail grew, the more it became a distinguishing feature of the comet. The tail's size, shape, and brightness were directly related to the amount of material being released from the nucleus and the forces acting on the particles in the solar wind. For C2017K2, the tail became a visible reminder of the comet's activity growing larger and more complex as it neared its closest point to the Sun. The tail of C2017K2, like all comet tails, always pointed away from the Sun regardless of the direction the comet was travelling. This behaviour is due to the forces acting on the particles released from the nucleus. The solar wind, a stream of charged particles emitted by the Sun, interacts with the gas and dust released by the comet, pushing these particles away from the Sun. This interaction causes the tail to always point in the opposite direction of the Sun, forming a distinctive linear structure that can extend for millions of kilometres. The pressure of sunlight also plays a role in shaping the tail. The lighter dust particles are pushed more easily than the heavier gas particles, which results in a tail that is primarily composed of dust and gas spread across a long distance behind the comet. For C2017K2, this behaviour was observed as the tail grew longer and more diffuse, becoming an increasingly prominent feature as the comet approached the Sun. The tail's appearance also varied depending on the composition of the material being released from the nucleus. In addition to dust and gas, comets often release a variety of other materials, including organic compounds and small solid particles. The presence of these compounds in the tail can influence the tail's colour and brightness. Some comets, for example, have been observed to exhibit blue tails, a result of the release of carbon monoxide and other gases. The colour and brightness of C2017K2's tail were influenced by the specific materials being released from its nucleus, with the dust particles scattering sunlight and contributing to the bright visible appearance of the tail. The presence of organic compounds in the tail also provided scientists with important clues about the composition of the comet's nucleus and the chemical processes at work in the early solar system. The growing tail of C2017K2 was not only a visual spectacle, but also an important scientific tool. As the comet's tail expanded, it provided scientists with an opportunity to study the properties of the gas and dust released from the nucleus. Observations of the tail allowed researchers to gather data on the composition of the comet, the types of volatile materials present, and how these materials interacted with solar radiation and the solar wind. The study of the tail also provided insights into the processes of sublimation and outgassing, helping scientists refine their understanding of how comets behave as they approach the Sun. In particular, C2017K2's tail offered a unique chance to study the behaviour of a long-period Comet 1 that had never been observed before at such close range. By analysing the tail, scientists could learn more about the chemical and physical properties of comets from the outer reaches of the solar system, and how these comets evolve as they interact with the Sun. In addition to its size and structure, the tail of C2017K2 also served as an indicator of the comet's activity. The larger and more pronounced the tail, the more material the comet was releasing, and the greater its overall activity. For C2017K2, the growing tail was a clear indication of the increasing outgassing as the comet moved closer to the Sun. The intensity of the tail's growth reflected the increasing rate of sublimation, as more ices in the nucleus were heated by the Sun. The tail with its dust and gas particles became a visible record of the comet's interaction with solar radiation, providing a direct measure of the forces at work as the comet moved through the solar system. As C2017K2 approached perihelion, its tail became one of the most defining features of the comet, a bright and visible marker of the comet's dynamic activity. For scientists, the study of the tail provided a wealth of information about the dynamics of cometary outgassing, the composition of the comet's nucleus, and the processes that govern the formation of comets. The tail was a direct result of the volatile materials being released from the nucleus, and its structure and size were influenced by the interaction between the solar wind sunlight and the material in the comet's coma. C2017K2's tail in particular was a remarkable feature that not only served as a visual representation of the comet's activity, but also contributed to the broader understanding of cometary behavior and the role of comets in the solar system's evolution. As C2017K2 moved closer to perihelion, the processes of outgassing and tail formation continued to unfold in remarkable ways. While the visible coma and tail of a comet are often the most striking features, these are only the most immediate results of a complex interaction between a comet's nucleus and the Sun's radiation. Beneath the surface, other processes were at work, particularly the role of dust and gas in shaping the comet's activity. The dust particles released from the nucleus during outgassing play a critical role in the comet's appearance. These particles, often small grains of rock and ice, are pushed away from the nucleus by the pressure of sunlight. As they are released, they begin to scatter sunlight, causing the tail to glow. The larger and more active the comet, the more dust it releases, and consequently the larger and brighter the tail becomes. In C2017K2's case, the amount of dust released from its nucleus was substantial, leading to a larger, brighter tail. The dust tail, which tends to be more diffuse and elongated than the gas tail, follows a slightly different path. While the gas tail is shaped primarily by the pressure from the solar wind and sunlight, the dust tail is shaped more by the comet's motion through space. The dust particles, though still pushed away from the Sun by solar radiation, are also influenced by the comet's velocity and trajectory. The dust trail left behind by C2017K2, like the comet's tail, pointed away from the Sun, but it often appeared more spread out and less defined. The amount of dust in the tail could vary depending on the size and composition of the dust particles released. In some cases, the tail could appear to split or form distinct features, especially when the comet was releasing a large amount of dust at once. The dust particles that make up the tail can provide important clues about the composition of the comet's nucleus. These particles are often made up of a mix of water ice, organic compounds, and rocky material. By studying the spectral signature of the dust in the tail, scientists can learn more about the chemical makeup of the comet. In the case of C2017K2, its large size and early outgassing suggested that its nucleus contained a particularly rich mixture of volatile materials. The tail, which continued to grow and evolve as the comet approached perihelion, offered a chance to study these materials in greater detail. The dust particles combined with the gas released from the nucleus were a direct reflection of the comet's internal composition. For astronomers, the ability to study the dust in the tail was just as important as studying the gas in the coma, as the dust can tell a more complete story about the materials that make up a comet. Another important aspect of the tail is the interaction between the gas and dust particles and the solar wind. The solar wind, a continuous stream of charged particles emitted by the Sun, interacts with the gas and dust particles released by the comet, pushing them away from the nucleus. The solar wind is a significant factor in shaping the structure of a comet's tail, and in some cases it can create interesting phenomena such as tail bifurcation, where the tail splits into multiple branches. The solar wind's influence on C2017 K2's tail could be seen in the way the tail stretched out behind the comet as it moved through space. The solar wind also interacts with the gas particles in the coma, creating a pressure that further pushes the gas away from the comet. This results in the coma expanding, sometimes forming a large diffuse cloud of gas that surrounds the nucleus. For C2017 K2, the interaction between the solar wind and the gas and dust released from its nucleus played a significant role in shaping the overall appearance of the comet. As the comet got closer to the Sun, the solar wind grew stronger, and the tail became more extended, stretching further behind the comet's path. The role of solar wind in shaping the tail highlights the dynamic nature of comets. As they travel through the solar system, they interact with the Sun's radiation and wind, which influences their behavior. While the Sun's radiation is the primary cause of outgassing, the solar wind can enhance or modify the tail's structure. In the case of C2017 K2, the comet's early activity and the increasing intensity of outgassing led to a tail that was particularly prominent and complex. As the comet continued its journey through the solar system, its tail evolved, becoming more visible and more pronounced as it approached perihelion. The tail, always a striking feature of a comet, provided scientists with a visual record of the forces at play within the comet's environment. One of the key factors that contributed to the tail's appearance was the comet's size. As discussed earlier, the nucleus of C2017 K2 was much larger than that of most comets, measuring approximately 20 kilometers in diameter. This large nucleus meant that the comet had more surface area from which gas and dust could be released, and it also allowed the comet to sustain its activity for a longer period. The greater surface area contributed to the intensity of the outgassing, which in turn created a larger coma and tail. For C2017 K2, the size of the nucleus allowed it to produce a tail that was far more visible than that of a typical comet. The larger tail indicated the increased activity of the comet and the greater amount of gas and dust released into space. As C2017 K2 continued its approach toward perihelion, the forces at work in shaping its tail became more pronounced. The increased solar radiation caused the nucleus to release even more gas and dust, which grew the coma and extended the tail further behind the comet. The interaction between the released particles and the solar wind led to the continuous stretching and elongation of the tail, creating the visual signature that astronomers associate with comets. The large tail of C2017 K2, along with the visible coma, became one of the defining features of the comet, making it a subject of great interest for astronomers and the public alike. The structure of C2017 K2's tail also provided valuable insights into the nature of the comet's outgassing and how its materials interacted with solar radiation. The tail was composed not only of dust, but also of gases including water vapor, carbon dioxide, and organic compounds, all of which were released from the nucleus as the comet approached the Sun. The gases formed the bright coma around the nucleus, while the dust particles scattered sunlight to form the visible tail. The tail's growth and structure were directly linked to the comet's composition, which included a rich mixture of volatile materials that responded rapidly to solar heating. C2017 K2's tail was an important feature for scientists studying the dynamics of cometary activity, as it provided a visual representation of the processes occurring within the comet's nucleus. The study of C2017 K2's tail not only gave scientists insight into the comet's current activity, but also offered clues about its history and origins. The tail of a comet is a direct reflection of the materials that have been preserved in the comet's nucleus, and by analysing the composition of the tail, scientists can learn more about the conditions in the early solar system. The dust particles in the tail, combined with the gases released from the nucleus, provided valuable data on the chemical composition of C2017 K2. The study of these particles is crucial for understanding the role that comets played in the formation of the solar system and the potential delivery of organic compounds to Earth in its early history. For C2017 K2, the growing size and complexity of the tail was a striking feature of its evolution. The tail not only grew larger as the comet approached perihelion, but also became a powerful visual and scientific indicator of the comet's dynamic behavior. The tail shaped by the interaction between the comet's outgassing and the solar wind served as a record of the forces that were at work in the comet's environment, providing astronomers with a unique opportunity to study the processes that govern cometary activity. The study of C-2017 K2's tail and outgassing behavior required advanced observational techniques from both Earth-based and space-based telescopes. Given the increasing intensity of the comet's activity as it approached perihelion, astronomers had a unique opportunity to monitor its behavior with unprecedented detail. Ground-based telescopes were able to track the comet as it became visible to observers on Earth, and its rapidly expanding coma and tail provided important data on the processes occurring within the comet's nucleus. These telescopes, including some of the largest observatories in the world, were able to capture detailed images of the comet's coma and tail, revealing how the gas and dust particles interacted with solar radiation and the solar wind. In addition to ground-based observations, space-based telescopes provided invaluable data on C-2017 K2's behavior. Instruments aboard space telescopes, such as the Hubble Space Telescope, offered detailed spectroscopic data that allowed scientists to analyze the chemical composition of the comet's coma and tail. Spectroscopy, a technique that splits light into its component wavelengths, enables astronomers to identify the specific gases present in the comet's outgassing. By analyzing the spectral lines emitted by these gases, scientists were able to determine the composition of the material being released from the comet's nucleus. For C-2017 K2, these observations revealed the presence of water vapor, carbon dioxide, methane, ammonia, and a variety of organic compounds in the coma and tail. These compounds are typical of comets, but the specific mix of volatiles present in C-2017 K2's outgassing could provide important clues about the conditions in the early solar system and the types of materials that were preserved in the comet's nucleus. The combination of ground-based and space-based observations allowed scientists to develop a detailed picture of C-2017 K2's behavior as it moved through the inner solar system. The ability to track the comet's outgassing in real time provided valuable insights into the dynamics of sublimation and the way that solar radiation and solar wind influenced the shape and structure of the comet's coma and tail. These observations also allowed scientists to study the evolution of the comet over time as its activity increased and its tail grew longer. The near-continuous monitoring of C-2017 K2 gave astronomers an opportunity to observe how the comet's outgassing varied with its distance from the Sun and to see how it responded to the changing solar conditions. The observations of C-2017 K2 also helped scientists refine their understanding of the factors that drive cometary outgassing. One of the key aspects of a comet's activity is its proximity to the Sun. As a comet moves closer to the Sun, the increase in solar radiation causes more of the comet's ices to sublimate, leading to a larger coma and a more prominent tail. The amount of material released by the comet is influenced by the size and composition of the nucleus, as well as the amount of solar radiation it receives. The early onset of outgassing in C-2017 K2, which was detected while the comet was still far from the Sun, indicated that its nucleus was made up of more volatile materials than typical comets. The ability to observe this early activity provided valuable insights into how comets begin their journey toward the Sun and the factors that determine the timing and intensity of their outgassing. In addition to studying the comet's outgassing behavior, astronomers also used these observations to learn more about the physical properties of C-2017 K2's nucleus. While comets are often too distant and faint to study in detail, the close approach of C-2017 K2 allowed scientists to gather data on the size, shape, and rotation of the nucleus. By analyzing the light curve of the comet, which measures the variation in brightness over time, astronomers were able to estimate the rotation period of the nucleus and gain insights into its shape. The light curve can reveal how the comet's surface reflects sunlight and how it changes as the nucleus rotates. For C-2017 K2, The light curve suggested that the nucleus was relatively large and likely irregularly shaped. This information helped scientists understand how the rotation of the nucleus influenced the comet's outgassing, with some parts of the surface being exposed to more solar radiation at certain times, leading to uneven sublimation and asymmetric activity. In addition to examining the comet's surface properties, scientists also studied the dust released by C2017 K2 to learn more about the composition of the nucleus. The dust particles released by a comet are typically made up of a mixture of rocky material and ice, and the specific properties of the dust can provide insights into the types of materials present in the comet's nucleus. By analysing the dust in the tail, scientists can determine the mineral composition of the comet and learn more about the processes that shaped its formation. The presence of certain minerals such as silicates and carbonates can provide clues about the conditions in the early solar system and the processes that led to the formation of comets. The dust released by C2017 K2 was particularly valuable because it allowed scientists to study a long-period comet that had never been observed before at such close range. The detailed observations of C2017 K2 also provided valuable information about the broader population of comets in the solar system. Comets are considered some of the most primitive objects in the solar system, containing materials that have been largely unchanged since the formation of the solar system. By studying comets like C2017, K2 scientists can learn more about the early conditions in the solar system and the processes that led to the formation of planets and other celestial bodies. The observations of C2017 K2's outgassing tail and dust composition helped scientists refine their models of comet formation and evolution, offering a better understanding of how comets interact with solar radiation and the solar wind over time. These observations also raised important questions about the role of comets in the history of the solar system. Some scientists hypothesize that comets may have played a key role in the delivery of water and organic molecules to Earth during the planet's early history. This hypothesis is based on the idea that comets, which contain large amounts of water and organic compounds, may have been responsible for supplying these essential materials to the early Earth. By studying comets like C2017, K2 scientists can learn more about the composition of these objects and how they might have contributed to the conditions that allowed life to form on Earth. In the case of C2017 K2, its early activity, large size, and rich volatile composition made it a particularly valuable target for scientific study. The detailed observations of the comet allowed scientists to learn more about the processes that drive cometary activity as well as the materials that make up the nucleus. The combination of ground-based and space-based observations provided a comprehensive view of the comet's behaviour and helped scientists refine their understanding of comets and their role in the solar system's evolution. C2017 K2 continued to captivate astronomers as it approached its closest approach to the Sun, revealing more about its enigmatic features. One of the most intriguing aspects of this comet was the unusual features observed within its coma, the cloud of gas and dust surrounding the nucleus. Unlike typical comets whose coma is usually symmetric and fairly uniform, C2017 K2 displayed a distinct asymmetrical structure. The irregular shape of the coma was a key indicator of the comet's active outgassing and the processes occurring within its nucleus. This asymmetric coma suggested that the comet's nucleus was not perfectly uniform, with areas of greater and lesser sublimation across its surface. This uneven heating likely resulted from the varying exposure of the nucleus to the Sun as it rotated. As different portions of the nucleus received more or less solar radiation at different times, the rate of outgassing from each region varied, leading to the irregular shape of the coma. The observation of such an asymmetrical coma was one of the unique features of C2017 K2 and provided important insights into the internal structure of the nucleus. In addition to the asymmetry in the coma, scientists also observed the formation of multiple components within the coma itself. In some comets, the coma consists mainly of a single diffuse cloud of gas and dust, but C2017 K2's coma displayed a more complex structure. There were hints of distinct knots or clumps of material likely formed by variations in the release of gas and dust. These knots could indicate that the outgassing was not uniform across the nucleus, but rather occurred in bursts or from specific regions. Such observations suggested that there were dynamic processes occurring within the comet, perhaps linked to internal structures such as pockets of volatile material or variations in the porosity of the nucleus. These irregularities in the coma also pointed to the possibility that C2017K2 had a more complex surface than typical comets, with variations in the materials present and the rate at which they were sublimating. This discovery added another layer of complexity to our understanding of how comets behave as they approach the Sun and undergo outgassing. The unusual features of C2017K2's coma also raised important questions about the comet's age and history. The uneven outgassing and the complex structure of the coma suggested that the comet's nucleus had been subjected to a variety of conditions over its long journey through the solar system. Unlike comets that frequently pass through the inner solar system, C2017K2 had not been in close proximity to the Sun for billions of years. This means that its nucleus had been preserved in a more pristine state than that of a typical short-period comet. However, the varying levels of outgassing and the observed asymmetry in the coma indicated that the nucleus had undergone some degree of alteration as it moved through the solar system. The differences in sublimation rates and the presence of distinct knots or clumps within the coma suggested that the surface of C2017K2 was not entirely uniform, but had been shaped by the comet's long journey. These observations provided valuable clues about the history of the comet and the conditions that led to the formation of its nucleus. As C2017K2 approached perihelion, the point of its closest approach to the Sun, the irregularities in the coma became even more pronounced. The increasing intensity of outgassing driven by the intense solar radiation led to an even greater release of gas and dust from the nucleus. The expanding coma grew larger and more diffuse as more material was released into space. This expansion was not uniform, however. The irregular shape of the coma became more evident as parts of the coma grew denser, while other parts became more diffuse. This further emphasized the asymmetric nature of the comet's outgassing and pointed to the complex internal processes at work within the nucleus. The shape and size of the coma were continually evolving as the comet moved closer to the Sun, providing astronomers with an ever-changing picture of the comet's behavior. The asymmetry in C2017K2's coma also had implications for the formation of the comet's tail. As the gas and dust particles were released from the nucleus, they were carried away from the comet by the pressure of sunlight and the solar wind. The tail made up of these particles always pointed away from the Sun, but the asymmetry in the coma meant that the tail also displayed irregularities. The tail was not perfectly straight or evenly distributed as the varying rates of outgassing led to differences in the density and distribution of material. This was another striking feature of C2017K2's behavior and added to the complexity of its appearance. The tail structure was influenced not only by the forces of solar radiation and solar wind, but also by the internal characteristics of the comet itself, as indicated by the irregularities in the coma. Beyond the immediate features of the coma and tail, the observation of C2017K2's outgassing and its asymmetrical coma had broader implications for the study of comets. The study of irregular outgassing patterns in comets had been an ongoing area of research, as understanding the distribution of volatile materials within a comet's nucleus can provide valuable insights into the processes that drive cometary activity. Comets, particularly long-period ones like C2017K2, are thought to be some of the most primitive objects in the solar system, containing materials that have remained largely unchanged since the formation of the solar system. By studying the outgassing behavior of C2017K2 and the structure of its coma, scientists could refine their models of how comets evolve and how they interact with the Sun's radiation. The fact that C2017K2 displayed such unique features in its coma also highlighted the diversity of cometary behavior. While many comets display relatively simple symmetric comas, C2017K2's coma was more complex with irregularities that suggested an internal structure more varied than that of typical comets. The differences in outgassing rates across the nucleus were likely due to variations in the distribution of volatile materials or differences in the porosity and texture of the surface. These findings underscored the idea that no two comets are exactly alike, and each offers a unique opportunity to study the dynamic processes at work in the solar system's most primitive objects. The irregular coma of C2017 K2 also provided a reminder of the challenges and rewards of studying comets. While the growing coma and tail of C2017 K2 were a visible and dynamic feature of the comet, the underlying processes that shaped these features were far more complex. The varying rates of outgassing, the asymmetric release of gas and dust, and the evolving shape of the coma all pointed to the fact that comets are not static objects. They are dynamic, evolving bodies that respond to the forces of solar radiation, internal processes, and their own orbital characteristics. Understanding the behavior of comets like C2017 K2 is essential for understanding the early solar system and the role that these objects played in shaping the formation of planets and other bodies. As C2017 K2 continued its journey through the solar system, scientists continued to monitor its behavior, eager to learn more about the forces at work within the comet's nucleus and how these forces influenced its coma and tail. The observations of C2017 K2's asymmetric coma, irregular tail, and complex outgassing patterns provided a rare and valuable opportunity to study a comet in detail. The data gathered from these observations helped astronomers refine their understanding of cometary activity, the composition of cometary nuclei, and the processes that govern the behavior of these ancient bodies. The unique features of C2017 K2's coma served as a reminder of the complexity of comets and the importance of continued observation and study in unraveling the mysteries of the solar system's most primitive objects. C2017 K2's passage through the inner solar system provided more than just a rare opportunity to study its immediate activity. It also raised important questions about the broader role comets play in our understanding of the solar system's formation. As one of the largest long-period comets observed in recent years, 2017 K2 offered a unique glimpse into the nature of comets that originate from the distant Oort cloud, a spherical region of icy objects far beyond the orbit of Neptune. The Oort cloud is thought to be the source of many long-period comets, those that take thousands or even millions of years to complete a single orbit around the Sun. These comets, which spend most of their time in the cold reaches of the outer solar system, are believed to have remained relatively unchanged since the formation of the solar system. Studying comets like C2017 K2 is crucial for understanding the conditions in the early solar system, as these objects are essentially time capsules preserving information about the primordial materials that existed when the Sun and planets were first forming. The unique characteristics of C2017 K2 made it particularly important for understanding the composition and evolution of comets from the Oort cloud. Comets are often described as the building blocks of the solar system, containing water, organic compounds, and other volatiles that may have played a significant role in the delivery of key materials to the forming planets. Some researchers hypothesize that comets, including long-period ones like C2017 K2, may have contributed to the presence of water and organic molecules on Earth, potentially playing a role in the origins of life. By studying the composition and behavior of C2017, K2 scientists could gain insights into the types of materials that were present in the early solar system and how they were distributed throughout the inner and outer planets. For example, the gases and organic compounds released from C2017 K2 during its outgassing provided valuable clues about the types of volatiles that were present in the comet's nucleus, and these compounds can offer a direct link to the conditions in the early solar system. C2017 K2's behavior also shed light on the long-term dynamics of comets and how they evolve over time. Long-period comets like C2017 K2 spend the majority of their orbits far from the Sun, where they are effectively frozen in a state of dormancy. As they approach the Sun, the heat from solar radiation causes them to heat up, and begin to sublimate, releasing gas and dust that form the coma and tail. The amount of activity a comet displays depends largely on the composition of its nucleus and the amount of volatile material it contains. C2017 K2's early onset of outgassing, combined with its large size and rich composition, meant that it remained active over a longer period than typical comets. This extended activity, along with the comet's large and irregular coma, provided valuable information about how the physical properties of a comet affect its behavior as it moves through the solar system. The study of C2017 K2 also provided insight into the processes that shape the evolution of comets in the Oort cloud. Over the course of its long journey, C2017 K2 had been subjected to many gravitational influences from nearby stars and the Sun, which may have altered its orbit and brought it into the inner solar system. These gravitational interactions, often referred to as perturbations, are thought to play a key role in the evolution of long-period comets. As these objects interact with the gravitational fields of other stars and planets, their orbits can be altered, causing them to move toward the inner solar system. For C2017 K2, the path it took through the solar system provided valuable data on how comets from the Oort cloud are influenced by the gravitational forces of other bodies. This knowledge is important for understanding the dynamics of the Oort cloud and the mechanisms that govern the orbits of comets in this distant region. One of the most important aspects of studying long-period comets like C2017 K2 is the opportunity to understand the history of the solar system itself. Comets are often considered the leftovers of solar system formation, as they are composed of materials that were not incorporated into the planets and other bodies. These materials, including ices, dust, and organic compounds, are thought to have been preserved in the cold reaches of the outer solar system, offering a snapshot of the early solar system. By studying the composition of C2017, K2 scientists could learn more about the materials that were present in the primordial solar nebula, the disk of gas and dust that surrounded the young sun and gave birth to the planets. The composition of a comet's nucleus reflects the conditions in the outer regions of the solar nebula, which were much colder than the inner regions where the terrestrial planets formed. Comets therefore provide crucial information about the conditions that existed far from the Sun where icy bodies like C2017 K2 formed. In addition to providing insights into the early solar system, the study of C2017 K2 also helped refine our understanding of the broader population of comets. While many comets have been observed as they approach the inner solar system, comets, like C2017 K2, which originate from the distant Oort cloud, are much rarer and more difficult to study. These long-period comets are often faint and distant, making them challenging to observe in detail. However, the close approach of C2017 K2 provided scientists with an invaluable opportunity to study a long-period comet at close range, allowing them to observe its outgassing behavior, analyze the composition of its coma and tail, and track its evolution as it approached the Sun. The data collected from C2017 K2 helped scientists refine their models of cometary behavior and gain a better understanding of how comets from the Oort cloud interact with the Sun. One of the key findings from the study of C2017 K2 was the fact that comets, even those from the distant Oort cloud, can exhibit significant levels of activity even before they reach the inner solar system. The early outgassing observed in C2017 K2 was a significant departure from the typical behavior of comets, which usually only begin to show signs of activity once they are much closer to the Sun. The fact that C2017 K2 began to sublimate and release gas and dust at such a great distance suggested that the volatile materials in its nucleus were particularly sensitive to solar radiation. This discovery raised important questions about the composition of long-period comets and how their materials differ from those of short-period comets, which are more commonly observed. The ability to study the early activity of C2017 K2 provided valuable insights into the dynamics of comets that are just beginning their journey through the inner solar system. As C2017 K2 continued on its path toward perihelion, scientists continued to monitor its behavior, eager to see how it would evolve as it neared the Sun. The data collected from this comet would help refine our understanding of the processes that govern cometary activity and offer new insights into the conditions that prevailed in the early solar system. C-2017 K2's passage through the inner solar system was an opportunity to study one of the most ancient and primitive objects in the solar system, offering a rare glimpse into the past and helping to answer some of the most fundamental questions about the origin of our solar system. The insights gained from this comet's behaviour would contribute to a broader understanding of the role that comets play in the solar system's formation and evolution, offering a window into the distant past of our cosmic neighbourhood. The passage of C-2017 K2 through the inner solar system was not only an opportunity to observe its behaviour, but also a chance to gain a deeper understanding of cometary evolution. Comets are often considered relics of the early solar system, preserving materials that predate the formation of the planets. The study of long-period comets like C-2017 K2 offers a rare glimpse into the conditions that existed in the early solar system, far from the Sun where icy bodies formed. Long-period comets originate from the Oort cloud, a distant and largely unexplored region at the edge of the solar system. It is believed that the Oort cloud contains countless icy objects, remnants from the early solar system that have remained relatively untouched by the Sun's radiation. The fact that C-2017 K2 originated from this region means that its composition could provide crucial information about the materials that existed in the outer reaches of the solar nebula, the disk of gas and dust that surrounded the early Sun. In many ways, studying long-period comets like C-2017 K2 allows scientists to observe the early conditions that led to the formation of the planets and other solar system bodies. By analysing the composition of C-2017 K2's nucleus and the volatile materials it released during its approach to the Sun, scientists can gain insights into the types of ices, dust and organic compounds that were present in the early solar system. These materials could have played a key role in the formation of planets and moons, as well as the delivery of water and organic compounds to the inner solar system. The potential contribution of comets to the origins of life on Earth is a topic of significant interest, as comets contain a wide variety of organic molecules that could have served as the building blocks of life. C-2017 K2's early outgassing behaviour provided an unexpected opportunity to study a long-period comet in greater detail than most comets allow. While short-period comets are often observed repeatedly over several orbits, long-period comets, like C-2017 K2, are only visible for a brief period of time during their first pass through the inner solar system. This means that observations of long-period comets are limited, making each encounter an important event for scientists. The early outgassing observed in 2017 K2 was significant because it allowed scientists to study the comet's behaviour at a stage when many other comets would still be dormant. Most comets begin their outgassing process only when they are close enough to the Sun for the heat to cause their volatile ices to sublimate. However, C-2017 K2 displayed signs of activity at a greater distance than expected, suggesting that its ices were particularly volatile or that its surface structure allowed for early sublimation. The study of this early outgassing offered a unique opportunity to learn about the processes that govern cometary activity and the factors that influence when and how comets begin to show signs of life as they move through the solar system. The composition of C-2017 K2's nucleus played a crucial role in the comet's early activity. Like most comets, C-2017 K2's nucleus was made up of a mixture of water, ice carbon dioxide, methane ammonia, and dust. However, the precise distribution of these materials and their volatility determined how quickly the comet began to sublimate as it approached the Sun. The fact that C-2017 K2 began to show signs of outgassing at a greater distance from the Sun than typical comets suggests that its nucleus contained more volatile materials that were more easily vaporized. The interaction between the Sun's radiation and the volatile ices within the nucleus triggered the early outgassing, causing the release of gas and dust into space. This early outgassing process provided valuable insights into the properties of the comet's nucleus and how its materials interacted with solar radiation. Another significant aspect of C2017K2's activity was its large size. The nucleus of C2017K2 was approximately 20 kilometers in diameter, much larger than most comets observed to date. The large size of the nucleus allowed the comet to sustain its activity for a longer period before the loss of material began to significantly affect its behavior. In general, the larger the nucleus of a comet, the more material it can release, resulting in a more prominent coma and tail. C2017K2's large size meant that it could continue to produce significant amounts of gas and dust as it approached the Sun, contributing to the comet's brightness and visibility. The larger the nucleus, the greater the surface area available for outgassing, and as a result, C2017K2's coma and tail became more expansive and visible even from great distances. The study of C2017K2 also helped improve our understanding of the evolution of comets as they move through the solar system. Over time, the nucleus of a comet loses material through sublimation as it passes close to the Sun. This loss of material changes the comet's surface properties and can lead to a decrease in activity as the nucleus becomes smaller and less volatile. The fact that C2017K2's activity was sustained for such a long period, even before it reached the inner solar system, provided scientists with valuable insights into how long-period comets evolve over their lifetimes. This information is important for understanding the broader population of comets in the solar system, as long-period comets make up a large portion of the cometary population, but are far less studied than their short-period counterparts. By studying C2017K2 and other long-period comets, scientists can learn more about how comets evolve over their long journeys and how they interact with the Sun's radiation. C2017K2's passage through the solar system also underscored the importance of continued monitoring and observation of comets. While many comets are observed on multiple passes through the solar system, long-period comets like C2017K2 offer only a brief window of observation. As the comet travels through the inner solar system on its first pass, it offers a rare opportunity to study its outgassing behavior, the composition of its nucleus, and the dynamics of its coma and tail. However, once the comet leaves the inner solar system, it becomes too faint to observe, and the opportunity to study it is lost for potentially millions of years. The brief window of observation for long-period comets makes each encounter an invaluable scientific opportunity. The data collected from these observations helps scientists refine their models of cometary behavior and understand the processes that govern their activity and evolution. As C2017K2 continued its journey through the solar system, scientists remained focused on gathering as much data as possible. The comet's passage through the inner solar system provided a rare and valuable opportunity to study a long-period comet in detail. The observations made during this period of increased activity allowed astronomers to learn more about the physical properties of the comet's nucleus, the processes that drive cometary outgassing, and the composition of the materials that make up the comet's coma and tail. These observations also helped improve our understanding of the broader role that comets play in the solar system's evolution and the history of the solar system itself. C2017K2's activity was a reminder of the dynamic and ever-changing nature of comets. These objects, which originate in the cold, distant regions of the solar system, are constantly evolving as they interact with the Sun's radiation and the solar wind. Their behavior is influenced by their composition, size, and orbit, and studying these factors provides insights into the formation of the solar system and the processes that shaped its development. C2017K2's passage through the solar system with its unique outgassing behavior and large size offered valuable clues about the early solar system, the volatile materials that were present, and the role that comets played in the delivery of key materials to the planets. As C2017K2 passed its closest approach to the Sun perihelion, its journey through the inner solar system reached a critical turning point. The peak of a comet's activity occurs as it nears the Sun, and for C2017K2 this was no exception. The comet's outgassing intensified, producing a more expansive coma and a tail that stretched out into the solar wind. After its perihelion, C2017K2 began to move away from the Sun, transitioning to a new phase in its orbit. The forces that had been driving its activity, solar radiation and solar wind, began to weaken as the comet receded into the outer reaches of the solar system. With less solar energy available, the rate of sublimation from the nucleus began to slow. As a result, the coma and tail gradually dissipated, and the visible signs of activity that had been so prominent in the inner solar system started to fade. This shift in the comet's behaviour marks a natural cycle for long-period comets. As they travel away from the Sun, they lose their most visible features and their activity decreases. The nucleus, once actively releasing gas and dust, becomes dormant again as it moves back into the colder outer regions of the solar system. While comets like C2017K2 may not exhibit visible activity for long periods, they remain dynamic objects. They continue to orbit the Sun, and their behaviour can change when they approach the inner solar system once more. However, for C2017K2, the passage through the inner solar system was a brief but significant moment in its long journey. The comet's activity, its early outgassing, and its unusually large tail provided valuable insights into how comets evolve over time, and how they interact with the Sun. As the comet moves further from the Sun, the most immediate effect is the fading of its coma and tail. These features, which are powered by the Sun's radiation, are most active when the comet is close to the Sun, and receive less energy as the comet travels farther out into the solar system. The process of sublimation slows, and the gas and dust that form the coma and tail gradually disperse into space. This transition also marks the comet's return to the outer solar system, where it will spend the majority of its orbit. For C2017K2, the outward journey will take it far beyond the orbit of Neptune and back into the cold depths of the Oort cloud where it originated. The Oort cloud is a vast spherical region of icy objects that surrounds the solar system, extending far beyond the planets. Comets like C2017K2 are believed to have originated in this distant region, and their long elliptical orbits bring them into the inner solar system only once, before they return to the outer reaches for millions or even billions of years. C2017K2's journey, however, is not just a simple cycle between the Sun and the Oort cloud. While it will remain dormant for long periods, the comet's passage through the solar system has left a lasting impact on our understanding of cometary behaviour and the dynamics of long-period comets. The data collected from C2017K2's approach provided scientists with a rare opportunity to study a comet from the Oort cloud in detail. This particular comet, with its early activity, large size, and complex outgassing patterns, served as an excellent example of how comets evolve and how they respond to solar radiation over time. Its study has given astronomers a better understanding of the composition, activity, and life cycle of long-period comets, and has contributed to our broader understanding of the formation of the solar system. C2017K2's early outgassing, observed well before it reached the orbit of Jupiter, was a key feature of its passage. Comets generally begin to show signs of activity once they approach the inner solar system, but C2017K2's early onset of sublimation suggested that its nucleus contained more volatile materials than many other comets. The ability to study this early activity provided insights into the composition of the comet and the conditions that influenced its behaviour. It also raised questions about the factors that determine when and how comets begin to sublimate as they approach the Sun. The study of this early outgassing process will help scientists refine their models of cometary behaviour and improve their understanding of how comets from the Oort cloud interact with the Sun's radiation. As C2017K2 continues on its orbit and moves farther from the Sun, the comet will once again enter the dormant phase of its journey. However, its passage through the inner solar system will leave a lasting legacy in terms of scientific data and the insights gained from studying a long-period comet. The data collected during the comet's approach has contributed to our understanding of the processes that drive cometary activity, the composition of cometary nuclei, and the role that comets play in the solar system's formation. In particular, C2017K2's large size and early outgassing behaviour have made it a unique subject of study, offering valuable clues about the properties of comets that originate from the outermost reaches of the solar system. For astronomers, the study of long-period comets like C2017 K2 is a reminder of the dynamic nature of these ancient objects. While comets are often considered relics of the early solar system, they are far from static. Their behavior changes over time, influenced by their proximity to the Sun and the materials within their nuclei. The passage of C2017 K2 has provided astronomers with an unprecedented opportunity to study a comet in its active state, gaining insights into its composition, its outgassing behavior, and its evolution over time. Although this comet will remain distant and inactive for many years to come, the knowledge gained from studying its journey will continue to shape our understanding of comets, the solar system, and the processes that govern their behavior. Looking ahead, scientists will continue to monitor long-period comets as they make their way through the solar system. While these comets are fleeting visitors, their passages provide invaluable data that can help refine our models of cometary activity and provide a better understanding of the solar system's formation. The study of comets, particularly those from the distant Oort cloud, is essential for understanding the building blocks of the solar system and the role that these ancient objects played in its early evolution. C2017 K2, with its early outgassing, large size and complex behavior, has provided an exceptional opportunity to study a long-period comet up close. As the comet fades into the distance, its contributions to science will endure, enriching our knowledge of the solar system and the mysteries that still await discovery.